Good morning and welcome to day 3 of the SERC SRR and the ERIC SRR. Today we're focused on the student projects in the graduate research fellows presentation, but this year we have something new. We decided to start off with a couple of tutorials. And so if you're joining this tutorial, I'm Tom McDermott. I'm joined by Peter Billing, Tim Sherburne, and Megan Clifford. We're going to present to you the culmination of a pretty large body of work on cyber resilience that we can kind of call a standard methodology now, a novel and standard methodology that's ready for transition. And so we'll launch right in. Next slide, please, Tim. So a lot of different people and a lot of different programs in this space and a lot of different support from different government agencies contributed to this work. And so you're going to see the outcome of it. So here's the list of the folks on the team. I'd also like to recognize Barry Horowitz at the University of Virginia, because this was kind of his idea at the start. Next slide. So the motivation today is the advanced persistent threat in critical systems. And so one of the things that we learned along the way was, how do we deal with this particular problem? Many of us in the cybersecurity domain are aware of the advanced persistent threat in information systems, but they exist in critical systems too. And it's pretty well acknowledged, at least in the government domains, that we can't completely protect against these type of threats. And so we have to switch to a model where we become resilient to these types of threats, which is the focus that we have today. And so if you think about the process of attacking a critical system, in this report on real Russian threat activity in an American nuclear plant kind of summarize the process that you have to go through. There's a process where the threat does social engineering to learn about the system, and then physical engineering to understand how to exploit the system and get into it, and then a lot of testing to figure out the vulnerabilities in the system so that they can deliver their exploit, and then the actual attack scenario in that space. And so cybersecurity traditionally focuses on analysis of that process, which is kind of bottoms up. What we are actually interested in here is what that means in terms of loss, so we can prioritize our response to those threats, and then how we execute the outcomes of that. And so in this particular case, we lack models that would describe the impact of a generic type threat in terms of outcomes on the system. And then finally, resilience. So how do we make sure that the system remains available or recovers or adapts in the presence of a threat, which needs to be designed in and tested in, and also has to be defined by requirements and performance measures. And so we've really been interested in that bottom side in terms of this methodology. Next slide, please, Tim. So going back into some history, in 2016, I was at Georgia Tech, and Barry Horowitz and Peter Billing, the team, they were at Virginia. And so we started looking at this problem of, how do we protect critical systems like the drone that you see here from cyber attack. And our understanding from a systems engineering point of view was that we had to address the behaviors, not just the physical components of the system. And so assurance in these type of critical systems is quite difficult. There's physical points of entry. They have off-the-shelf systems in them. The presence of the insider threat can change those systems or the function of them. And so actually doing that and protecting or preventing it in the assurance domain is practically impossible. But can you protect it or prevent it with a set of resilience features to ensure that even though the threat may exist in a critical system like that, it's still able to have an acceptable mission outcome, even if that's make sure you fly home and not somewhere else, that mission outcome can be defined in that space. So what we want to do is look at point defense, or defending the points of failure in the system, as opposed to perimeter defense, trying to keep the threat from outside the system. Next slide, please, Tim. So this scenario switches our mode of analysis upside down. So traditionally, cybersecurity analysis starts from the bottom, thinking about how the attacker can get into the system. We actually want to jump up to the top and think about how we protect the system and make it more resilient. And so that starts with, in a stakeholder point of view, not identifying vulnerabilities, but identifying what the nightmare scenario was. And in this particular case, it was an adversary taking control of the navigation system in the space. And then it moved from there into how do we detect and manage at the behavioral level, at the systems level, that particular system. And so in this case, there were 2 GPS units on this platform, one of them associated with the inertial system, one of them associated with sensor systems in the space. And so what we were able to do at the behavioral level was define a rather small and simple device that we could put on this aircraft to monitor the outputs, the behavior of the outputs of these 2 GPS units, and then switch them if one of them happened to be performing abnormally, as opposed to even knowing if it was being attacked or not. And so we found this to be a very effective methodology for protecting platforms like this at a relatively low cost. So as we went into this, we over time started to determine, well, these little behavioral based mechanisms, you may describe them as a device, but you can also describe them as simply a design pattern that goes into these systems, and that those design patterns could be placed into a system. And so what you would do is you would raise the bar of entry to the threat. So can you protect everything? Can everything be resilient? You're not necessarily going to know up front, but if you design enough of these things, then you raise the barrier to entry for the attacker. And so we want to maximize the uncertainty in the attacker by employing design patterns that make the system more resilient to those types of modes. Next slide, please. So this concept, this pattern, we call it a Sentinel, and it's really 2 patterns that exist in the system. And so you can think of this as a system to be protected, and in system engineering terms, that would be a systems model of a system to be protected. And that system is typically in these domains a control system. So it operates off of layers of control and feedback in that space. And then you can think of the system to be protected also having a pattern associated with it called a Sentinel. And the Sentinel measures the behavior of the system, and it provides detection and control over things if a threat is detected or any type of abnormal. So you can apply this thinking in a safety mind or any other kind of fault pattern. And so the Sentinel is responsible for that monitoring and recognizing the anomalies in the system, and then kicking off a reconfiguration of the system. And so the further pattern is called a resilience mode. And so a resilience mode is a separate function that's added into the system or device or component that when activated by the Sentinel changes the configuration of the system or perhaps the behaviors of it in order to allow the system to maintain its availability or its control or other things like that. So these 2 patterns, the Sentinel and the resilience modes, are the things that we want to introduce into the system engineering process and come up with a rigorous way to model them, which we'll show you the details of in a bit. Next slide. So this work has been applied to many different domains over the history. So we talked about the drone that we started off with, but it's also been experimented with in ship control systems, in 3D printers, in police cars, in industrial control systems. In fact, it's been there's some components that have been patented and applied into a company that supports this. Also, feeding up to the human level. So these control loops expand from the device up to the human controllers, and so with human factors experiments, and also in a concept of network munitions in a what's more of a system of systems mode, which is the case study that we'll show you on later on today. Next slide, please. So one of the things that is helpful for us as we go through this process is when we start thinking about these Sentinel patterns and these resilience modes, there's a number of different types of these things, but it's not an infinite number of types of these things. And so there's a finite number. They can be described in terms of their capability. And so this is a list of them that's documented in the NIST 800-160 Volume 2 standard, which is looking at resilience in cyber physical systems. And so the idea here is in a system engineering process, you can select these things and you can select these patterns and you can model them and you can apply them into your design and you can test them. And so it takes the problem from what seems to be very complex down to something that is easy to fairly rigorously model. And so you'll see those approaches as we go through it. Next slide, please. So what do we mean then by system resilience? Well, what we want to do is we want to maybe compare system assurance from system resilience. And so system assurance is what we typically do in response to cyber attacks and cyber threats. And system assurance is the justified confidence that the system functions as intended and is free of exploitable vulnerabilities in that space. And so functions and intended and free of exploitable vulnerabilities represent the system's highest level properties. You know, the free of exploitable vulnerabilities is a property that we can't necessarily guarantee in all systems at all times, and particularly against determined attackers who are changing their behaviors every day. It's also kind of a static property. So assurance is evaluated against the system as built. And so we have a particular problem of what happens if the system is not built yet. How can we assess assurance if the system is not built yet? So we have to jump to different modes. And this is where resilience comes into play, or resilience engineering. So resilience is the capacity of a system to maintain state awareness and to proactively maintain a safe level of operational normancy in response to anomalies. And so the resilience of the system is pretty agnostic to the attacker. You know, it functions based on patterns. And so you can define attacks, but you can define classes of attacks and classes of responses and assume they'll happen. Resilience is also a dynamic functional property of a system that can be modeled against any type of pattern that would affect it. And so it can expand out to safety, security, fault tolerance. You know, the number of these patterns is a small enough set where we can model them into the system. But to be effective about resilience, we need tools that allow us to reason about the resilience of a system and to reason about them as functions of the system, particularly control functions. Next slide, please. So as we moved on in this research and started to develop these methodologies, we got really interested in how we can apply these much earlier into the system lifecycle. So if assurance is primarily going to be going to happen at the end of the development lifecycle, when you have a design that you can test, structurally test, then we'll be too late and we'll be stuck in this mode of always trying to catch up with the threat. If resilience can be designed way up into the front of the system, particularly even pre-requirements in that stage, then we can have much more flexibility in terms of cost versus functionality decisions in that space. And so in this slide, there's a bunch of acronyms at the bottom that aren't necessarily explained, but there's standard processes, some of which are really useful at the as design life cycles, like hazard analysis and formal methods. And some of them are much more useful at the beginning of the life cycle, like STPA SEC, the System Theoretic Process Assessment, which is actually looking more at large-scale systemic loops in that place. And so, so what we're going to show you is a process that primarily runs up at the front end, all the way from concept development down through the initial design of a system that's effective at making resilience decisions into the design. Next slide, please. So this is the last one I'll talk to, and just to give you a mental model of what we're going to talk about for the rest of this morning. So we talked about bottoms up and top down in this domain. And so our typical way of thinking about cyber attacks as is a set of attackers who enter a system through a set of system assets or components. And so this might be a network interface, it might be a computer, a FPGA. So at the bottom level, there's sets of components that have vulnerabilities in it, and the system, the threats will enter through those points. But their goal is not just to enter the system, their goal is to compromise some mission of the system in the end. And so these threats propagate from these physical entry points into the information assets, whether it's, excuse me, data or software, and compromise that. And then they propagate up to the system functionality. And so then they compromise a function or a behavior of the system that then propagates up to the user of the system in their operational use and tasks, which then can propagate up to the mission level. So if you ask the question, what if we started at the top and we understood what were the most critical mission objectives that we had to be resilient for or protect against, and then worked our way back down to a system decomposition using system engineering processes? What are the operational models that define those tasks? What are the system behaviors and activities that define those functions down to the system assets? Then we would be able to apply these patterns. And so if you look in the middle here, the system functions, these are functional models of the system. You know, in system engineering land, we would call these activity diagrams or functional flow block diagrams or IDEFO diagrams. You know, as we go through this normal process of defining and decomposing system functions, we want to design the functions at that level to incorporate these Sentinel type behaviors and these resilience patterns. And so the process that we're going to see as we go through this is that derivation process to capture these things into a formal model that we call the mission aware Metamodel. And so I'll stop there and I'll turn it over to Peter.
Good. Thank you, Tom. Much appreciated. So yeah, I'd like to continue the thought that Tom was just on, of the question of how would we ultimately begin to model and reason about the function of a system with regard to properties like resilience. So this has been something that has occupied our attention for some years now, and we think we've made some progress in defining a good methodology, and that's what we'd like to share with you this morning. The challenge, as Tom pointed out, is that in trying to reason about functionality in the context of resilience, we're doing it for systems that don't exist yet, right? So we would like to be able to do this at the before requirements are chosen. So not only does the system not exist yet, but we're in the business of defining what it should be in a lot of ways. So our process is something that is supported by a number of different tools, and we're going to be walking through the tools and methods in the abstract, and then ultimately in the particular with a case study. So just as a preview there, that everything that I'm about to launch into will be at kind of one level of abstraction, but then later we'll bring in a detailed case study so that you can see how this all comes into being in the context of a system. So the notion that we have for reasoning about the functions of a system is really based off of employing three notional groups of stakeholders: the blue team, the gold team, and the red team. and then asking each group of stakeholders to answer only questions that they're capable of answering. For instance, the blue team, which is the system and mission owners, we're going to ask them questions about what they care about in terms of, as the owners of the system and mission, in terms of what they need to have happen in terms of system performance. So each team is going to be asked a set of questions that we think is appropriate to their knowledge base and background. And those questions are going to be supported by some tools and methodologies. And so we'll end up walking through what each of those are. But in a nutshell, I can describe it this way, that the blue team, the system and mission owners, they're going to be given a structured elicitation process from the safety community, which we'll go through in just a moment, called Stpa. And what they're going to be asked to do is to give us an understanding of what are the losses that they care the most about. So Tom mentioned nightmare scenarios, and that's really what we're trying to understand from the blue team. What is it that is necessary for mission success that the blue team wants to identify as its top priorities? So we are asking for a prioritized list, because ultimately, you know, if we're talking about something like resilience and the kind of design patterns that Tom mentioned, in the end, there's another team that's maybe not listed here, the green team, that's in charge of the money. You know, there are limits to how widely you can, in any system, can think about applying these design patterns. Budgetary limits, there are potentially limits on system performance associated with adding things like Sentinels and reconfiguration options and the redundancy that is implied there. All of that has a system performance impact. So there will be a trade-off between the prioritized list that the blue team ends up producing and the realities of the situation viewed from system performance or monetary objectives. But what we're going to ask the blue team to do is produce that prioritized list, and then that becomes input for our gold team. This is where the systems engineers come in, and the systems engineers are in charge of doing several things. One thing is producing a model of the system, maybe kind of as is, and models that incorporate notions of resilience. So the systems engineers are involved in the architectural scoping of potential resilient solutions. And we're going to ask them to do that in the context of model-based systems engineering. We'll describe exactly the kinds of models we're thinking about, but all of our concepts here could translate to any kind of tool set that involves Mbse. So we'll have a particular one, but this is a general concept. So the challenge, of course, with modeling systems with Mbse in general is that if you're modeling a very complex system, then the task becomes pretty daunting, right, in a lot of cases. So you can imagine trying to do this for a drone, model the entire system, perhaps becomes exponentially more complex as the weapon system, the vehicle, the critical system itself grows in complexity. But this is where the prioritized list and the focus on resilience come into play, because we can bound the activity that we're asking of the gold team based off of, well, what you're modeling are the aspects of the system that have to do with resilience. And in particular, focusing attention on the kinds of losses and the prioritized list of concerns that were expressed by the blue team. So finally, I'll mention the red team. So the red team is our in-house adversaries, and we can think of a red team in a normal sense as being people that come in and, you know, given a software base for a system, then engage in you know, various hacking attempts to identify vulnerabilities or review of the code, and in terms of static analysis or a number of different activities that involve looking at the the actual system from a software perspective. Well, here, if we're thinking about this kind of process, as Tom said early, then we don't have that software base for the red team to work with. But we still need help reasoning about the vulnerabilities of the system post-resilient design. So can the red team help us understand the any potential vulnerabilities that we've introduced, anything that we've added to the attack space of the system because of our resilience actions? Can they help us understand what the resilience designs may not be addressing, but that are still kind of intersecting the priorities of the blue team? So that's what we're asking the red team to do. And to do that without a system that exists, we of course need to provide them with the models of the system. So we can do that in Mbse terms. We can also begin to translate those models into other forms. For example, GraphML, to give a graphical representation of the system, which is more amenable to algorithmic analysis, doesn't require as much of an understanding of SysML on the part of the red team as would otherwise be the case if we fed them the models directly. And that would allow for cross-referencing with things like MITRE's attack database, KPEC, and other kinds of databases that have captured the tactics and techniques of adversaries, the experience of attacks on particular kinds of hardware and so on, that might be useful cross-references in thinking from things from a vulnerability perspective. So that interaction with the red team is not something that we're going to focus on today, but that's a topic we'd be happy to pursue with others who are interested in this. And I will say that that kind of notion of red teaming systems has taken a lot of advance in recent years, and with tools that are out there and programs that are out there like the Navy's CVAST. Next slide, please. So I'd like to show our overall methodology for thinking through and ultimately getting to requirements for operational and cyber resilience in just a moment. But I'll just say that with the blue team, what we're assuming is that the blue team has engaged in a process of mission engineering. So there's a very important tie between the notions of mission engineering and our methodology. So we're going to assume that the system and mission owners in thinking through their priorities have mapped those priorities, as Tom said, all the way starting from the mission. Excuse me one second. So next slide, please. So we're going to assume that that activity has been completed, and the blue team is in a position to reason about what they view as the loss scenarios with respect to the missions, with respect to the systems that are most important to them. And then we can follow a process that we call the cybersecurity requirements methodology. And I'm showing kind of a simple version of Csrm right now, and we'll come back to it as we layer in some complexity from several other perspectives as we go along over the course of the first part of our tutorial this morning. But I think you can catch the nature of the methodology from the figure here, that we're engaging the blue team, and that's the colored blue box, in an operational risk assessment. We may feed them tools and system descriptions produced by the systems engineers. Those are the gold boxes. We're getting the prioritized resilient solutions and using those as the basis for an initial design. And then there's a vulnerability assessment. And at some point we end up transitioning this kind of iterative loop as we're going through the system V to other activities like V&V. So, and all of the aspects of the use of these kinds of this methodology and our thinking in general will be something that we'll try and illustrate at a couple of different points on the system V as we go along. So next slide, please. So what's supporting the CSRM? And the answer is it's something that we call mission aware. Mission aware is a concept that folds together a number of different elements. So you can see 3 of the elements shown here, and there are still others that we're kind of not including for simplicity right now, but model-based systems engineering, something called Stpa sec. And that's a methodology on its own from a different source, and notions of resilience concepts, which our foundation there would be the Sentinel-based resilience concept that Tom walked through, but potentially other concepts from MITRE, anything that you have in mind could in principle fit into this general kind of thinking. It might require a little bit of work. Next slide, please. So, so I want to talk through all 3 of those elements: the Mbse, the Stpa, and the how resilience concepts ultimately get folded in with those 2 things and formed into something. And what's the something? It ends up being an Mbse metamodel. And the question, I think there are several questions that come to mind when I say that, perhaps like, well, what is Mbse in some sense, and what is a metamodel? But let me illustrate that just as a starting what I mean. So one could think of a high-level model of the system as being something that covers the structure of the system. So what is it? But also its behavior. What does it do? And then relates those 2 things to sets of requirements that specify, why the system is doing what it is, and ultimately relate everything to verification and some ability to test that the system is meeting the requirements through its structure and behavior. So this is a top-level meta model, and it's meta in the sense that it's something from which models can be derived for specific systems. I think you wouldn't want to, let's go to the next slide, look at something quite that high level to try and do that for a system, but would need additional detail. And so here is another meta model, again, something that from which a lower level specific model, a specific model for a particular system could be derived. This is from the corporation called Vitex Corporation, and this is their Genesis product. So we'd like to offer this as a kind of foundation for what we'll end up showing in a few minutes. The Vitex Genesis meta model here has a lot of properties that are similar to what we would expect the open source standard SysML version 2 to ultimately get to. So right now, it's not quite there, and SysML v2 is still on its way, but it's still several years out. So what are the properties that we like about Vitex model? We like that it provides the capability to model systems in a hierarchical sense, and perhaps capturing some of the dynamic elements of systems. So this kind of compact meta model here that you see has several other things of note. Well, for one thing, that the aspiration here is that this meta model can really capture most systems. So it has a great deal of generality in terms of covering systems from an abstract perspective in a way that covers kind of all the basis for modeling systems, and to some extent the systems engineering process. So that's one aspect of it. Another aspect is, while it looks like a picture, it's actually software, and it comes with defined semantics and a real information model that gives meaning to each of the elements, each of the arcs. Now what's in it, all kinds of things, but you can identify things that relate to the structure of the system, to the functions, notions of states and resources and use cases, to requirements, to verification. So this is our foundation. This is not the ending point, just the starting point for us to make use of this. And again, as we'll look at the mission aware and see its Mbse artifacts, we could have taken other turns. So we could have used SysML. We could wait for SysML v2, but we've chosen to work with Genesis. If you're interested in these concepts and would like to explore doing mission aware in another tool set, that's something that we'd certainly be open to talking about. And at the end, Tom McDermott is going to talk a little bit about our efforts to transition this work and our willingness to engage in training. And that is a topic we can revisit if anyone's interested. Next slide.
Peter,
Yeah.
can I interrupt you for a quick question?
Yeah.
So Beth Wilson asked, in the Csrm step for verification, which you can cover here, do you see the red team engagement for early verification? So is the red team actually involved in that verification requirement step?
That's right. So, yeah, I'll let Tim take that question since yeah, we will ultimately get to maybe answering that in a context of our example. So Tim, do you want to take that and give a precursor?
Yeah, I mean, I give it
what you'll end up showing. So Beth, we're going to have a case study later, and so I kind of want Tim to address the question in general, but also maybe mention what we'll show in specific with regard to that.
Yeah, so I would just say, I mean, one of the definite advantages of, the model-based systems engineering and this, Peter was mentioning the CSRM and this multiple team view is that, each of the teams, the blue team, the red team, the systems engineers can all have a view of, of the model. And I mean, so the red team, like Peter's saying, we'll get to the specific examples, but, identifying, what are the key loss scenarios. And we will show that, based on those loss scenarios and these Sentinel patterns that, deriving specific verification requirements for those cases. So we do see, yeah, I hope I'm answering the question, but yeah, direct linkage in the model of, eliciting specific requirements to enable a Sentinel, for example, to maybe be able to detect a specific loss scenario and having verification requirements that actually has the test team verify that that loss scenario can be emulated in the system and verify the resilient mode does protect the system. So.
Yeah, let me just add one or two things. That first thing, it's a great question to think about to what extent are we ultimately doing this pre-requirements and iterating with aspirations about resilience in mind, but ultimately then getting to requirements that are bounding the design and implementation of the system. So some of the notion of verification at that level comes really early. We'll also get to a different notion of verification at the level of, say, developmental test. And that's something that we're going to speak about later.
Peter,
add that to there?
Yeah, so Beth asked another question. I think I'll take this on, but in the Metamodel, could we consider the nightmare scenario as a misuse case in the place of a use case in the diagram? And so I think you'll see later on the example that the attacker does have use cases in the model and that you can capture those. So, so we don't necessarily call them misuse cases, but just as a maintainer has a use case, an attacker has a use case in the model. And so it's you can capture that.
Yeah, very good.
Yeah, and those scenarios really are like those abuse cases are kind of we call them the loss scenarios. What are those key things we're worried about? And yeah.
Right, and at the same time, so we're as you'll see, Beth, that the loss scenarios are kind of guiding the way that we think about the resilience response, but we're careful not to pin the attacker down on what ways they could make a loss scenario unfold. So we try to make little assumptions about how the adversary might do something, and focus our assumptions and concerns and modeling on how our system could be affected in ways that would be undesirable. Good.
So she asked, can the use case be the loss scenario? And so I think when we show you the MA meta model, which we're going to do here in a second, you'll see how use cases and loss scenarios are linked together. So we can probably move on to the next slide, Peter.
Yeah, that'd be great. Great. So remember, we're combining three things to get to mission aware: the Mbse foundation, the notion of Stpa, and our resilience kinds of concepts. So Scpa is a methodology from the safety community, I think developed and certainly popularized and brought to life by Nancy Leveson and others at MIT. And the notion that they were pursuing was that if you were looking at something like an accident with aircraft, that one way to look at it is that's a confluence of random variables that have come together in an unfortunate way. But a more fruitful way to think about an accident would be, and this would be a loss, let's call it a loss. A more fruitful way of looking at a loss is not a collection of random variables coming together, unfortunately, but rather something that can be modeled in terms of hierarchical control, so that before we got to a loss, we were in a hazardous state of some kind, and then there was a transition from that state to the loss state, and influencing that transition is the environment, but also things like unsafe control actions. So if you want to think through the prevention of a loss, then reasoning in these kinds of terms might be particularly attractive and well suited to something like the resilience architecture that Tom introduced, because we can begin to think about system functions in terms of hazardous states, in terms of control actions, and these are all things that can be potentially monitored. And when we see ourselves going into a state, we can influence through the use of the Sentinel or reconfiguration, the transitions out of that state. Next slide, please. So it turns out that this kind of idea from the safety community of Stpa has been brought into the security community by Colonel Bill Young, who developed Stpa-Sec. And in a nutshell, I think it's fair to characterize Stpa-Sec's differences from Stpa as being the two largest ones I'd like to say are that it brings in adversarial causal factors. So it's not just nature that we're playing against or people making mistakes, but deliberate adversaries, and that lends a bit of a different character to the thought process, but nothing too fundamentally different. And then the notion that one should think about losses in the context of mission engineering is an incredibly important part of Stpa-Sec. So that's what we would like to do. We'd like to think about losses and have the blue team and our whole characterization of loss scenarios as something that is not specific to, say, a vehicle, but the use of the vehicle in the context of a mission, right? Good, next slide, please. So, so here's our, then we're going to transition to our mission-aware meta model. And the notion here is now we're combining the Metamodel that I showed earlier, top level view, with the notion of a loss scenario coming from Stpa, with the notion of resilient modes and a Sentinel, and all coming together. And this is what we would call mission aware now. And we'll show detail in just a second, but you can see the elements that I just described of the loss scenarios, and being something that we're attempting to protect against using a Sentinel system, which in this figure is shown as something external to the main system, but it can be integrated to any level. So this is just conceptual view. And then based off loss scenarios, and the detection of a possible evolution of a loss scenario, then we can switch to resilient modes, influence the way that the structure, the system is actively structured and operating at a particular time. So let's go to the next slide. And so here's the detailed view of mission aware. And again, this is pretty abstract. And Tim's going to walk through a complete example for a particular system. But what you can begin to see in this Metamodel is a number of different elements. So we've taken the functional elements and physical elements and interface elements that are sort of part of any kind of a system, and added to them all of the tannish colored elements that correspond to several different things. So we can see hazardous actions, hazards, losses, control actions, and so on, sort of towards the bottom right of the model. And all of that is, if you will, the Stpa part of or part of the Stpa contributions to mission aware. And then you can see resilient modes and Sentinel scenarios and remediation as being, these are things that and attack patterns and other things, and I'll mention those in just a second. So you can see that the Sentinel in our Sentinel-based resilience architecture has crept into this model as well. There's a little bit of subtle detail in this picture. Beth, that gets to some of your questions. If you want to see the roles of the three different teams, they're really, well, I guess the red team and the blue team are really highlighted because the systems engineers are, of course, engaged in building all of this. But you can see the red team and the role that they're playing, and that some of those tan boxes are outlined in red, and others are outlined in blue. So we're asking the blue team to help us identify what are the hazardous actions, hazards, and losses that should be of concern. And we're asking the red team to help us reason about what loss scenarios and remediations might be appropriate. So when they have identified something that could go wrong with a given design, can they help comment on a way to produce remediation that would be appropriate. There are other things in here, some dashed outlines that correspond to other ways of adding detail and folding in other aspects of kind of cyber defense and resilience generally. So one example is that we can extend our notions of resilience and that are captured in this kind of model to include other things that are more defensive or preventative in nature, such as cyber hygiene. And we've engaged in a project with MITRE and kind of exploring in cyber physical systems what's the potential interplay between hygiene practices, such as cyber hygiene practices, such as password updating and maintaining good control of passwords, and patching software and all the kinds of things that you would view as kind of basic measures of keeping control of your system, how those kinds of behaviors and practices can trade off against things like cyber resilience. Is there a question, Tom?
Yeah, so Brian Nolan asks, where does states come into play in this meta model?
Okay, you want to take that one, Tom? You're our state machine expert.
Yeah, so states would be represented in this meta model as part of the functional structure in the space. But at this point in time, since we're reasoning about these patterns in the functionality of the system, we're not to the point in the design where we actually explicitly represent states yet, but you could.
Yeah. Good. All right. Good question. And you'll get, yeah. I don't know if you'll have time at the end, Tom, to mention some of our work in trying to connect to that kind of reasoning. Let's go to the next slide, please. Oh, sorry, go back one slide, Tim. I got derailed in my segue. And my segue is to say that, there's one box that we really want to get to trying to think about how we're going to construct that. And that's the red requirements box. And the question is, so we have all of this kind of modeling, and it's sensible from the perspective of aligning with these methodologies, and it seems to come together well, but how do we really get to requirements in the end? And so let's delve into that a little bit. And the way, let's go to the next slide. The way that we have approached that question is to think more about resilience from an operational perspective. So we've come up with something called the Framework for Operational Resilience in Engineering and System Test, FOREST. And the notion in FOREST is that what we're going to do is decompose how systems operate as they undergo adversity and engage in hopefully in a response based off of resilience features engineered into them. So what that really comes down to is kind of saying that if we're going to have resilience, we have to think about things like loss scenarios, be prepared to develop whatever techniques that we can put in place to try and prevent those loss scenarios based off the kind of modeling we've just gone through. But we also need to think about how those systems, those features of the system, if you will, I guess is a way to put it, that are oriented towards resilience are really going to work in the context of a system. How does it all play out? And what are the elements associated with that? Because thinking through all of that kind of aspect of resilience unfolding in terms of the technology, the humans and the operators and the decisions that are involved, that's all got to happen for the resilience to be something that really can work as designed. So we've reasoned about it at one level, and now we need to think about it operationally. So the notion in FOREST is to break apart the idea of cyber resilience and to say, well, the first thing we're going to have to do is the system is going to need to have some capability of understanding when it's under attack. So it needs a capability of sensing when its functions have been disturbed by potential cyber attack. It needs to understand what the boundaries of that disturbance are, what systems, subsystems, and so on are affected, where to what extent can the effects of the attack be isolated, to what extent can it bring to bear potential resilience responses that have been engineered in. So different modes of operation like the inertial navigation that Tom talked about that would be appropriate for the attack as currently understood, and a number of different elements. So let's switch to the next slide, and I can walk through some of those in a little bit more detail. So these are things that we call the testable requirements elicitation elements. Although I have to confess that when we're speaking to the test community, we have a little bit different name for them that gets to test questions, and I'll get to test in just a few moments. So yeah, and of course the joke is that if we have a forest, we must have trees, right? So testable requirements, elicitation elements, trees. And we've talked about attack sensing, attack isolation, resilience response, but there are other things to think about as well that have to do with the interplay of information provided by the system about its resilience solution and ultimately decisions and operational performance of the system as it's as it's operating in a resilient mode. So for example, what in trees 4 and 5 and are kind of intertwined in the sense that what that's trying to get at is the notion of to what extent can we anticipate what a particular resilient response might give in terms of both impact on the attack and operational performance. So what information can the system, should the system provide, if we're getting at requirements, right, for projecting that? Are there simulations, are there models, are there characterization of performance that can be given? Are there recommendations for particular modes of operation that the system can provide? What kind of data flow goes to operators so that they can understand? So when we think about something like readiness for operator evaluations, so to what extent can we train our people? Should the system include a notion of people, the operators being trained or having experience or having capability to gain experience on the fly? So one example that we think about in these kind of later stages of the forest trees is the example of the UAV, and let's assume that our autopilot function has been compromised. Then a resilient response might be to switch to a different autopilot or change some aspect of the way that the autopilot is working. But as the pilot of a UAV, you might want to engage in a process of gaining confidence that that new mode of operation is actually going to fly the aircraft appropriately. So you might want to be able to observe it in a particular way. You might be able to see whether all the, you might want to be able to verify that the attack isolation has been performed appropriately by using the joystick to see, well, let me see if the control surfaces have been affected and so on. So that's the notion of forest and we're going to walk through details of what some particular requirements that could be elicited from this process, and even from a test perspective, look at what associated measures and metrics might be for testing such requirements. So this is the abstract, and we'll get to the concrete in just a moment. Let's go to the next slide, please. So so forest is something that we mean to be applicable throughout the systems V. We're going to look at it, as I just mentioned, in requirement setting in kind of the architectural stage, but we'll also look a little bit later at test. Next slide, please. So let's see. So I think this is my last slide before transitioning. So the one thing that we've thought through is, as one sits down to try and write requirements associated with operational resilience, how will we know that we're kind of covering what we need to cover? And the forest framework by itself with the trees is meant to provide something of an answer there, that that you need to consider sensing, isolation, evaluation, confidence, readiness, and so on. And each aspect of the forest framework needs to be considered. But another way to look at it is, well, to what extent are we covering the ilities and other notions of quality attributes that exist for systems, cyber-physical systems in particular, generally? So we've engaged in a process of cross-referencing the two things as shown here, and getting to an idea of, all right, well, are we actually covering all of the trees? Are we covering the quality attributes? And so we can look row-wise and column-wise and begin to fill in, to see coverage. We can walk through the exercise of thinking through requirements for accuracy, where those end up applying. And if you think about that, you might say, well, the sensing function needs to be accurate, the isolation function needs to be accurate. But when you move away to the other tree elements, perhaps those don't relate to accuracy as much. So this kind of chart is something that we've developed in the general for all systems. We would argue that that you might end up wanting to write requirements that correspond roughly with this. But we'll show you a particular example again in the context of a notional weapons system in just a few minutes. One thing I'll note is that in going through this kind of exercise, what you'll discover in thinking about setting requirements for your system is that that ultimately there will be things that are that ultimately would be testable in a technology sense, and there are other requirements that ultimately would be things that if you're going to test them, to what extent is the system meeting them, you're going to need the engagement of an operator. So this is a kind of first view of things like developmental test and operational test ultimately coming together, which is something we'll mention later as well. Good, so let's go to the next slide. And Megan, would you like to take over from here?
I can, thank you. And then too, just one other thing to note about the tree quality attributes is not only the system measure and the operative measure, but also too the design consideration or system limitation as well. And so we've also gone through and looked at that, where there might be a system limitation in order to consider as we're looking at the quality attribute type. So then moving forward, one thing that we're looking at is cyber survivability engineering. This is a slide by Steve Pitcher. And just to give some background knowledge here, the Deputy Secretary of Defense initially directed the Joint Staff to develop cybersecurity key performance parameters. And it was initiated when the Deputy Secretary of Defense was briefed on a cybersecurity report with a whole lot of people involved that really highlighted multiple weapon systems with vulnerabilities that should have been known and fixed prior to development, test, and evaluation. And even too, as they were continuing to look at the information, they were continuing to find that the fixes were not getting done throughout, and they were hard and costly. So a problem there was system survivability requirements not sufficiently being articulated for cyber attack prevention, mitigation, recovery, adaptation, and adaptation within the requirements document. So the goal for is that the end state for all Department of Defense weapon systems and supporting infrastructure are to be cyber survivable, commensurate with risk managed approach to countering a capable or determined adversary. And this is being done through a three-pronged approach through improving cyber survivability in new weapon systems, legacy systems, and Department of Defense installation of critical infrastructure. And cyber survivability is a property defined for weapon systems and the critical infrastructure on which those systems depend. And cyber survivability attributes are system capabilities which support and serve as indicators of cyber survivability. And the attributes also support 4 mandatory pillars on the system survivability key performance parameters. They prevent, mitigate, recover, and adapt. And the CSAs, or cyber survivability attributes, are selected for a system based on its cyber survivability risk category, which you see is right there next to the ICD at the top of the slide. And they require key aspects of the survivability problem domain. And the CSA is implemented for a system by incorporating the CSA-based language within that initial capabilities document, and it's incorporating, updating, and elaborating CSA-driven functional requirements in the capability development document as it evolves, building the required functionality into the system. And considering cyber survivability during the analysis of alternatives may actually reduce the acquisition costs and long-term costs, and can act as a suppressant for less mature or secure cyber functionality that creates a greater risk to mission assurance than its intended benefit. So what we're looking to do, and where a huge gap is to address as well, is not even in the draft C, as right at the beginning in the ICD, then folding into the analysis of alternatives, but then too specifically to the draft capability development document, which is to understand those resource mission risk implications of capabilities unable to meet the intent of the cyber survivability attributes, to then provide guidance to requirements writers on tailoring of the CSAs to support both the requests for proposal and the TEMP document, which is the test and evaluation master plan development, consistent with the updated cyber survivability risk category and intelligence cyber threat assessments at milestone A. And a gap to address here is just to ensure that the tailored cyber survivability attributes are sufficiently detailed to be measurable and testable to support mission completion in intended cyber contested environment to form the basis for the source selection criteria. So what we're really looking to do, and you can just jump to the next slide too, what we're really looking to do is to put forest and our trees to use in determining metrics to put into specification, then into test and evaluation for intentional design. And so here are the cyber survivability attribute top level requirements. This is the relationship between cyber resiliency constructs and cyber survivability attributes. And again, we're looking to determine metrics to put into specification and then into test and evaluation against CSA 07, 08, 09, and 10. And this is especially since these are supporting mission defense team efforts. So while some capabilities, as Peter touched upon before, may be fully automated, most require human intervention. So this really deals with the human intervening levels. And CSA 07 is that baseline and monitor systems and detect anomalies. 08 is to manage system performance if degraded by cyber event. 09 is to recover the system capabilities, and then the adapt portion, CSA or cyber survivability attribute 10, is to actively manage the system's configuration to achieve and maintain an operationally resilient cyber survivability risk posture. Next slide. And so then what we've done is we've looked at our different trees and loss scenario elicited requirements and where they map to the cyber survivability attribute. And again, I should note, while we are focused on cyber survivability attributes 07 through 10, we also are looking at where it maps well and can be defined into the other cyber survivability attributes as well. So for an example, what we've done and what we've looked at is we have our tree, our T1, which is the sensing, and you can see the requirement number and then the description. We'll just read the first one. It's the system shall sense, we have the ID name, loss scenario by monitoring either the link, the resource, or the function. And this type of requirement is a functional requirement, and it traces right back to the cyber survivability attribute 07.1, which is one of the cyber resiliency constructs on that the system shall monitor operational parameters, boundaries, and configuration controls. So in the next slide, we also have the resilient mode elicited requirements, which are our trees 5 and 6. So we have our confidence and our readiness. Just reading for an example again from the top one for our tree 5 and our confidence, the requirement number, and then the description: the system shall provide management control mechanisms for operators to gain confidence in, ID name, resilient mode, and that's also a functional requirement, and traces back to CSA 08.3, 4, 5, and 6. And with those are just the system shall maintain mission critical function in a cyber contested operational environment during, after observed anomalies. And then of course, also 4, 5, and 6. So we've really just been tracing it back to show so that we can put specification, these metrics into specification for test and evaluation. And then our resilient mode elicited requirements too for tree 7 and tree 8. And these are of course continuing to be developed, but this is for our use case for this time being. And so T7 execution, we can read that here too, that the system shall provide management controls for execution of the resilient mode operational, which is a functional. And you're more than welcome to look through the slides and also see too the performance types as well. And so the next slide are example elicited requirements for the system as a whole. The elicit system requirement sources. We're looking at our loss scenarios, which is the enable sensing and the isolation by Sentinel, and the associated resilient mode management, the enable, the disable, and the self-test. And then 2, looking at that remediation. So below is the remediation, and to the left, we look at the elicited system requirement by the loss scenarios and what it's elicited by. But the remediation just provides the Sentinel for protection against the loss scenario. So we have the requirement, our type, whether it is functional, and then 2, what it's elicited by from the loss scenario. And then the remediation, we've also drawn and traced that out so that it protects against the loss scenario, and also the associated resilient mode, what is elicited, and the requirement that it's then drawn to as well. And with our quality attributes and metrics, which is the next slide, we've also been tracing and looking at some of the different and various resilience methodologies that have been utilized to measure system quality attributes, just such as safety and consequence containment of human errors, while aiming to provide a descriptive framework for partitioning resilience design as they relate to test opportunities. So one aspect of the research is diving into the quality attribute measures and metrics. And a quality attribute is a measurable or testable property of a system or realized non-functional requirement that's used to evaluate the performance of a system, and they're architecturally significant. By definition, an architectural mechanism is a structure whereby objects collaborate to provide some behavior that satisfies a requirement of the problem. And we're specifically interested in those mechanisms that significantly affect
Let's see, so Megan is frozen. Am I frozen as well?
No, you're good, Peter.
Okay, so let's move. So thank you, Megan. That's great. You're frozen, but I think you froze at just the right time as we're segueing to the next slide. Let me just mention a couple of things, and then we're going to get to the case study. So first, that all of the notions in Forest have also been kind of folded into the definition of the Csrm. So I don't think we need to dwell on that because we've walked through it. So let's go to the next slide. And then I want to make a quick point or two about test before we get to the case study. So the notion is that Forest is a useful construct for setting requirements, but also for thinking through test. Let's go to the next slide. And I just want to give a little bit of flavor to what are the issues associated with test and cyber resilience of weapon systems or cyber physical systems. So, the problem is if we write down requirements for resilience that are very high level, like the system shall have resilience with respect to cyber attack, it doesn't give us the basis for perhaps for design, but certainly not the basis for test, right? Like how would we actually test a requirement like that, or test a system against a requirement like that? And how are we going to think about the whole question that we've been wrestling? How do we reason about systems early on? So with developmental tests, then Megan talked a little bit about the measures and metrics associated with cyber resilience, and what we think Forest provides is a way of getting at what those things are. Megan gave a bit of a preview, and I'll just mention one other thing. But in the in thinking about something like developmental testing technology, we also will see that when with a topic like resilience and thinking about things in force terms, the human and operators and the whole perspective of operational test begins to come in strongly as well. So there's a nice kind of integrated view of test that naturally emerges from thinking through this. So let's go to the next slide, and I'll just mention, that we won't walk through this slide here, but just to mention that we've done quite a bit of thinking about the notion of what are T&E considerations, test and evaluation considerations for each aspect of the tree in the force methodology. So you've seen some of that kind of come out in particular examples, and you'll see some as well in what Tim does. Next slide, please. So I think the final or penultimate point I want to make about forest and test is just that in thinking about testing for cyber resilience, you have to understand that ultimately it's a different kind of activity than testing maybe for other properties of a system. A lot of properties of a system can be tested by dropping the system on its upside down, or heating it up, or shooting at it, or applying various inputs and seeing how it responds in terms of outputs. With cyber resilience, in something like a weapon system, what we're attempting to understand and test is how the system responds to its internal states, finding themselves suddenly in an undesirable position, or something that they weren't designed to operate in this particular state. So more maybe than other kinds of system properties for resilience, we need to think about having the ability in a test support system to configure the internal states of a system, to have emulation and control over what the system states are in a very unnatural way, right? That corresponds to the loss scenarios, corresponds to what might happen as a loss scenario unfolds. Again, we don't have to model the attack, but we do have to model the consequences of the attack, and even emulate the consequences of the attack, so that we can then see how do the resilient modes of operation unfold. Is the Sentinel able to detect that configuration that we've just established? Does it engage in an appropriate resilient mode of operation? Does an operator understand what's going on? What do they think about the whole situation? So I think you can get a sense of the intertwining of technology and people when you start to consider questions like that. So next slide, please. And then, finally, I'll just mention that we have extended or folded in these notions of test into the mission-aware Metamodel. So all of these considerations are part of our kind of overall Metamodel, all the full complexity of it. And so that's something that's available, and we'd be happy to share with folks. So let's go to the next slide, which I think is the Silverfish case study. So, Tim, I'll turn it over to you at this point. You can walk us through that.
Okay, thanks, Peter. So, so to start with, just kind of give like a ConOps type of like overview of what Silverfish is. So it's a networked munitions system, and there's a network of these obstacle devices that are placed out in a field to be protected. And the idea is that they have a set of munitions on them that can be controlled by an operator, a mobile operator that has a control station that can fire these weapons, basically to protect a ground area against physical attackers. In addition to this fire control, there's a notion of situational awareness, and there's a set of sensors that are part of this system that provide the situational awareness. So there's a UAV, there's infrared sensors, and even within the obstacles themselves, there's acoustic and seismic sensors. So we have a idea of, you know, different sensors that can kind of fused together to provide an overall situational awareness view to the operator. So with that, we'll kind of get into the mission aware Mbse description of this system. Oh, sorry, one more thing, just briefly kind of to give a little, this is like a part of the user interface that we created an emulation of this system with a set of Raspberry Pis, and this was part of the user interface. So its idea, this grid is the field that's being protected. Each of these grids represents an obstacle, and these little dots in here represent the directional munitions, you know, whether they've been fired or are ready to be fired. And just some ideas of how big this protected area can be, and, you know, it's intended to protect against both vehicles and people. You know, vehicles, tracked vehicles can move at roughly the speed of, you know, 10 miles an hour. So just to give an idea, like, you know, a vehicle could cross this whole protected area within about 2.5 minutes. So now I want to walk you through the Metamodel, or the system model, which is based on the mission aware Metamodel, and it'll kind of organize that walkthrough in terms of the Csrm process here and the artifacts that are produced at each of these Csrm steps. So first off, mission engineering. So we have attempted to, you know, again, since this is a hypothetical system, so we kind of created a couple of different missions for Silverfish. And the idea based on where it's deployed, if it's an isolated area or more of an urban area. And so the idea that an isolated area is more, we were saying, is more likely to be, you know, vehicle-based attackers. Vehicles move faster. So there might be some different kind of the measures of performance for the isolated area mission might expect faster moving vehicles. So, you know, when we get to resilience recovery, it may need to be faster resilience recovery to account for faster moving vehicles, versus an urban area maybe where it's more expected to be person-based attackers to the field. And we may have different kind of recovery requirements. So the idea is that we just, you know, for our scenarios, have a couple different missions proposed, and we'll see that kind of can derive the performance parameters for some of the resilient modes that we define for the system. So let's get into, first of all, now the initial kind of system description in terms of the Mbse system description for Silverfish. So to start with, you know, we have kind of a behavior view. We started with use case kind of views. So everything from this, Silverfish is intended to be a rapidly deployable system. So we cover the deployment use cases where the system is moved from some depot location, deployed into the specific field location, and when the mission's over, you know, undeploying the system as well. The key kind of functions for Silverfish itself is to monitor the field using the situational awareness, and if necessary, to protect the field with the fire control. This kind of question came up. We also include, you know, use cases kind of for mission aware, like protecting Silverfish from, you know, from cyber attackers, and how, you know, depending on the scenario, how the technician who does the deployment. If the deployment is tampered, how is the technician, sorry, I keep bumping the key there, how the technician may be involved in notification of the attack, or the operator in the case of the situational awareness or fire control. And then finally, also in kind of including the tester, and specifically, verification of the cyber resilience mechanisms built into the system, and the ideas of, like Peter was mentioning, this, the test support system. So from the use cases, again, this is just kind of a snippet of some of the high-level requirements that were derived for the system. High-level functional requirements, some of the performance requirements in terms of timing and sizing of the system, how many obstacles, how many, it's a battery powered system, how many days of continuous operation are expected. So so just want to give a snapshot here of the various types of systems requirements that we've captured for Silverfish. Next, we'll kind of move to the kind of architecture view of the system description. And here, I know this is probably kind of tiny to see here, but just like a physical block diagram. So at the left here is the system context, so Silverfish system in the middle here, and seeing the things that interact with Silverfish, from the human operators and technicians that interact with it, the UAV as a separate kind of system that is managed by command and control, but has an interface to feed, the images and analytics into Silverfish. Like I mentioned, we have the mission aware or the Sentinel subsystems monitored as a kind of a separate system that interacts with Silverfish, and also showing the kind of the test support system, those interactions with Silverfish. To the right here, we kind of go inside of Silverfish here, and we see the various control stations, the links, the wireless radio relay links to the set of obstacles and sensors. Now, as part of more of a detailed view of the behavior, again, this is just kind of a snip here to show you that we have, tried to model the behavior here and model it in in terms of a control structure here. So that is some of the kind of extensions we did to the Metamodel, that these items that move between functions of the system, we model them as specifically as control actions and feedback kind of items between functions. So there's a graphical view here, a snip of a graphical view, but then on the left here, also, out of the model, you can grab, tabular type views of the items in the database. So here, just showing an example of the system function to fire a weapon, and this is like the top level function. And since it's a layered kind of model here, just showing that we have the relationships that this top level firing, it's initiated by this fire control action, but then it's decomposed by these three functions, where part of it is the control station, the radio relay, transferring that message to the actual obstacle which implements the firing. So here again, just trying to show that you can iterate through the model here, and this is kind of the next level, lower level functions here of the control station, radio relay, and the lower level actions that trigger each of those lower level functions. So a brief description of the fire control, and then the bottom is kind of the monitoring the field kind of function.
Tim, just to add a comment, the previous question on state machine. So I think you can see here that using a functional flow block diagram with triggers, we're effectively defining the state-based behavior of the system as triggered by control attributes. So even though we're not showing it as a state machine diagram, we've captured it into these functional flow block diagrams.
Yeah, a good point. Thanks. Okay, so now, so I've kind of shown a view of the architecture and then kind of a behavior view. And a key thing of this meta model is, you know, the relationships between things here. And here, I just want to touch on the relationship between the physical view and the behavior view. That, you know, components perform functions. Functions, you know, input or output items, and those items are transferred over links, which are connected to components. So for Silverfish, just showing for specific examples here. So on the left here, these are kind of the components of Silverfish, kind of a brief description of the component, and, you know, what are the key functions performed by those components. The table on the right here, the links, you know, what components are connected by the link and which items flow over the specific links. So having this kind of knowledge represented in the model here, we'll see it becomes very useful knowledge to have when we get to the hazard analysis and the loss scenarios, that we know all the functions, we know which component performs the functions, the physical links, what type of information flows over those links. So that was kind of briefly our initial kind of system description. Now, based on that, we'll start to look at the specific risk assessment for Silverfish. And this is the Stpa kind of artifacts of, you know, losses, hazards, hazardous actions, and the relationships between them. So on the top left here, we identified kind of 4 key losses of importance, and, you know, loss of life to military or civilians, loss of you know, whatever assets are intended to be protected by Silverfish, and finally, you know, loss of classified mission, you know, the obstacles or the control stations, for example. Additionally, you know, the operators or mission owners, you know, are kind of give a priority kind of ranking of, you know, what's the most important thing that they're worried about for the Silverfish system. And then the next step is, you know, the set of hazards and how those hazards, we had like 3 here, kind of that, you know, misfiring of the weapon, excessive time to deploy the system, or excessive time to undeploy the system, and how those hazards could lead to these losses we defined here. And kind of the next lower level of, now what are the hazardous actions and how are those related? So finally, at the bottom here, I'll focus mostly in this example here about the incorrect firing of the munition. And here we also show, you know, besides the linkages between the Stpa artifacts, that we relate, you know, this hazardous action is a variation of the firing of the fire munition control action. So you can kind of imagine, if you do your control structure for the system, you have a defined set of control actions then for the system, and as you work your way through this Stpa process, you kind of have an inventory then. Okay, these are all the control actions I've defined. Now, have I considered, hazardous actions for all of those control actions, to kind of as a completeness check that, for all the things your system does. I mean, some actions maybe are not priority ones, but it's an inventory of things to keep track of as you do your system analysis. So the next step here is the potential resilience solutions. And the artifact there is this resilient mode, and how the resilient mode is related to alternate operations for components in the system, functions that can be system functions that could be recovered by a particular resilient mode. And then that resilient mode itself needs some sort of management operations, potentially. If it's a diverse redundant solution, maybe it needs management operations to enable or disable or switch between, active standby kind of operations. So again, specifically for Silverfish, again, this isn't necessarily everything, but we, examples that drew out interesting aspects for the system. So we looked at diverse redundancy for the radio relay network, the fire control stations. Like I mentioned, we had multiple types of sensors. There were redundant infrared sensors for the system, so we could play out different scenarios of comparing values between the different sensor types as a mechanism of detecting illogical behavior. So in addition here, like I mentioned, for each resilient mode, we're noting the relationship to the components that are impacted by that resilient mode, and this is showing ahead for the next step, but we'll get to the loss scenarios here in the next step here. So, like, the vulnerability assessment is next, and it's these kind of the final step of the loss of the Stpa, defining a set of loss scenarios as kind of a set of behaviors that are to be minimized or avoided in the system, and then a set of remediations. And the idea of the remediations, like Peter had mentioned, we are kind of capturing here a way of capturing defensive mechanisms that may be implemented, hygiene practices that may be implemented, Sentinel type protections that may be implemented, with the idea being it's maybe trade-offs that are done to to find the best set of security mechanisms for a particular system. Now, for example, again, this is, I know, very small here, but on the left here, these are the kind of set of remediations that we captured for Silverfish. So at the top here, like I mentioned, there's a set of hygiene practices that were noted for Silverfish, some forensic logging, separate accounts, for example, as good hygiene practices. So we know we have like this hygiene practices as a set of checklists within the model here. And this is noting which practices, which remediations were decided to be implemented for Silverfish, which made sense for this type of system. We also have some like defensive hardening mechanisms that were decided for Silverfish, like, for example, like tamper resistant hardware, for example, isolating the fire control station from the situational awareness station so that the fire control software could be hardened in terms of the development process. And then finally, the kind of resilient Sentinel-based resilience mechanisms as well. So it's kind of this balance between, hygiene practices, defensive mechanisms, and resilience modes that were decided for this case study. At the bottom here, these are the set of loss scenarios that were investigated for Silverfish. And here we capture, for example, this loss scenario of manipulated fire commands. We'll say that can definitely lead to, incorrect firing of the weapon. And we have a scenario where the isolation or the cause of that manipulated fire command in our example was because of the fire control station. So in this example, the reconfiguration, the resilient mode here was the diverse redundant fire control station.
Tim, quick question. This came from Beth Wilson, and she's asking, in prioritizing resiliency solutions, can we think of the lower priority solutions as a form of technical debt?
Possibly, I guess. It's all kind of the trade-off, between time and money, and the rating or the understanding by the mission on operator owners, like what's the most important thing. So yeah, possibly it's something that could be over time improved, I guess.
Yeah, I think so. You need to think about it as a trade space, obviously, in terms of cost and weight and other factors, but versus, because a resilience mode has an implementation and it has a cost, and so you can think about it architecturally, perhaps, and maybe you will leave the architectural capacity for that function in the system, but you won't actually implement the state machine for it, or the functional flow for that. And so that would protect you against technical debt if you found a threat that you need to add that on. But we haven't necessarily modeled that, but there's a couple different ways you can think about it.
Yep. Okay. Yeah, so now I just want to talk a little bit. So now we've gotten to the point in the model where we've defined a set of remediations and a set of loss scenarios. And I want to show kind of examples of these elicited requirements that, some constraints on the system, some functional requirements needed for the system, and then some additional performance requirements. And here we get at the, our tree-based CSA related performance requirements. So I have a little bit of an example for each of these types of requirements. So to start with, on the left here, we have a set of kind of system constraints. So again, if the Sentinel is going to be able to, monitor the system for illogical behavior, well, there needs to be, again, these are maybe kind of high level requirements, but there needs to be, so for the manipulated fire command, there needs to be some way of monitoring, the fire control actions. For some of these situational aware kind of loss scenarios, we need mechanisms to monitor consistency between the different sensors. So kind of just, thinking through making sure that the Sentinel and the system have mechanisms to work together. So I set up kind of constraint requirements to enable the Sentinel. It is kind of these first set of requirements. Additionally, kind of for the resilient modes that are identified, like I mentioned, that there needs to be some sort of management operations. Maybe it's some remediation, some resilient modes may be automatically managed by the Sentinel. Some may be more manually controlled by the operator. But in any case, there needs to be, management mechanisms enabled within Silverfish to control those resilient modes, whether it's controlled by the Sentinel or controlled by the operator. And then let's see. And then we have a set of requirements, again, just for these set of resilient modes for the system. We are eliciting requirements. You know, these are kind of more like Sentinel-based requirements. So what specifically is the Sentinel required to protect against? So high-level requirements there that relate to each loss scenario. That there's a, you know, the mission aware and the Sentinels are a type of system, and we need to define the requirements for, you know, what the Sentinels are supposed to be doing. In terms of performance requirements here, I got just a few examples of the CSA kind of, you know, quality attributes. So for example here, we talk about, you know, the trees for sensing, for example, sensing and isolation. So again, these are kind of performance requirements for the Sentinel here. But, you know, how quickly does the sensing need to happen? What kind of accuracy? And so just, these are kind of just some made up numbers here, but hopefully kind of gets the idea across that you need to define, you know, performance requirements for those steps of sensing and isolating. And here, kind of the tie back to our initial mission type measures of performance would influence these requirements. You know, depending on what the mission is, you know, the sensing requirements may be tighter or looser. Below here, I got another couple of examples here. Here it's now, you know, we talked about the test support system. And for example, you know, the test support system may measure, you know, the operator is evaluating, for example, the diverse redundancy, you know, to gain confidence. So what, you know, how quickly, how quick does the operator perform that, you know, or if you run the test with different sets of operators, do you see a similar timeliness, you know, for the operator making decisions, gaining confidence in the resilient mode? So finally, the last bit I'll touch on here is the verification and test aspects of the CSRM process. So as Peter mentioned, it's the verification requirements that verify functions, and here we say a loss scenario is a kind of function that we need to emulate so that we can verify that the resilient, you know, the Sentinel functions as expected and the resilient modes work as expected to minimize the impact of specific loss scenarios. So here we just have, as an example here, like the top level, there's like a verification requirement for verifying each of the kind of the Sentinel-based protections for each of the loss scenarios. And for each of those verification requirements, we talk about, you know, the test activity, this, and I'll show that in a minute, this test activity of verifying cyber resilience. And then, you know, what is the, you know, test configuration needed for that specific test. And so for Silverfish, it's, you know, it's fairly simple. Like I mentioned, there's really like the fire control functions and the subsystems that make up fire control versus the situational awareness components that make up the situational awareness functions. So here it's just, you know, noting the pieces, the components that are involved that'll need to be set up to perform these tests. And then the test activity here I've modeled it as a functional flow block diagram. I know it's very small here, but I'll kind of walk through here that the idea is it's kind of a iterative loop here. So for each loss scenario that's identified for your system, you want to go through, and there's kind of two branches here. The system kind of technical verification versus the operator kind of decisions and involvement. So each of these boxes here kind of represents one of the forest trees. So, for each loss scenario, we want to verify, the sensing, and we want to verify that the timing, whatever the timing requirements, that were specified, that we can test and that we're within spec for the timing and accuracy for sensing, for example. The isolation step, similar, we want to verify that we're within spec for whatever measures and metrics were defined. Now we kind of branch out for the options. We talk about, technically verifying the options exist. There may be some operational impact for the resilient mode. Maybe different people, different operators are involved. So, we have to have the operator kind of rating of the resilient mode, and so on through here, the isolation steps, the confidence building steps, and the readiness, and finally the execution of the resilient mode, or the enabling of the resilient mode within the system. So, like I said, it's kind of a generic loop for the test, but it's, what specifically is tested is, the requirements specific to each loss scenario and each resilient mode for that loss scenario. So that's kind of the end of what I had here for going through the case study.
A couple questions, Tim.
Yep.
So Paul McMahon asked, since we seem to be focusing on loss scenarios with this method, where do you factor in the likelihood of the cause?
The likelihood of the cause.
Yeah, so I'll answer that if you don't mind. So we have,
Yeah.
So in the red team and green team and gold team process, you have to identify the types of attacks that the system is potentially vulnerable to, even though we don't have the design yet. And so you have the ability to take, for instance, a known attack method out of KPAC and define that in the model, and then show how that particular attack behavior will flow through the control system in the model. And so Tim didn't show the example, but we do have those attack vectors modeled into the system. And so you can look at likelihood then, but since you don't actually know the part level vulnerabilities in the system yet at this level, you have to evolve that to risk later on as you go through the design process.
Yeah.
So Beth asked the question, can we craft the resiliency metrics in such a way to support integrated testing, the continuum of development tests through operational test?
Yeah, and I think this activity kind of starts to get at that there's certain, technical tests for the system here that you can actually measure things versus when the operator's involved and the operator's making decisions. So it starts to get at that division between, the development test and operational test. I don't know if somebody else has a better answer, maybe.
Well, I'll just add one thing to that, because I did mention that as a view that we're very supportive of, and the notion of even really thinking about requirements for elements of the technology that would end up supporting the operational test in the end. So, for example, the little reference architecture that we have for test includes notions of building into the system ways of interfacing with the operator for the purposes of evaluating resilience response that can be viewed as direct support of operational test. So these topics, when we engaged in thinking about tests, I'll just say about this as a backdrop, we were really working with the developmental test people, but we ended up walking down the path of that's much more integrated in nature and not being able to see clearly boundaries on this topic between developmental test and operational testing. You might otherwise see.
I can't hear, so I don't know.
Over.
Relevant for any reason. Question, what's the question?
So Mark Winstead noted you never talk of likelihoods on Arrakis. You speak only of possibilities. Yeah, I think that is kind of the point. Is we want to be able to enable those trades in the possibility space. So we just got a couple of minutes to wrap up here, Peter.
Okay, well, this is a transition topic. Do you want to?
Yeah,
I'll mention this one, and then turn it over to you. So yeah, we'd like to say a few words about transition of all this work to the community. And one way that we're walking down that path is with the DAU in developing courseware in support of their newly emerging cyber resiliency credentials. So all the things that you've seen, Forest, Mission Aware, all of those things are being folded in as aspects of a couple of courses, a foundational course and a practitioner course. And we hope to have further involvement in other levels and other degrees of specificity within cyber resilience. So I'll turn it over to you then, Tom, to mention some of the facilities.
So Peter, then I would just offer out. So as we worked our way through this process and developed a nice example model, we developed this tutorial to effectively show people you can walk through this resiliency problem as an end-to-end process. Taking this and encoding it into what DAU needs to teach in terms of acquisition people developing specifications and evaluating designs is the next step that we've been asked to go do. A further step we'll take that we haven't started yet is turning this into a multi-day training program that would be more focused on industry and government, but also more focused on the engineering details as opposed to just the acquisition details of this methodology. And so please let us know if you have interest in that. We've been talking to some stakeholders about putting together that training in both government and in industry. And we're also, we have a meeting next week to take this and talk about how we implement what we've done here into a formal guide that the government is putting together on cyber resiliency out of the office up in USD R&E in that space. And so, we'll hopefully have a guidance document to come out of this before too long in the space. So we're at that point now where we've matured a methodology using Mbse, and it can be demonstrated and it can be trained into a set of people that are doing model-based system design in these spaces. And so definitely at this point in time, we would like to welcome any transition opportunities that you might have. So I hope this was an informative tutorial for you, and I hope to be following up with you.
Thank you, everyone.
Would the guide be DoD?
So the question, would the guide be DoD only or available for industry? I don't know yet because the meeting is next week on that. The guide's being developed, I believe, by MITRE, and we'll be putting input into it. It's focused on the defense community. Is it releasable to industry or not? I assume it will be, but we'll have to wait and see on that. Okay. So we're at the end of our time. Thank you all for joining us, Peter, Tim, Megan, and thank you all for participating in this. And we hope you enjoyed it. Should close this down.